Alright, so we're on to our continuing our lesson on electrochemistry. So last day we discovered that metals like to give up their electrons. That's what makes them metals. So we had a little diagram of the periodic table, and we saw that metals are the majority of the periodic table, and they're elements that like to give up their electrons. In fact, that's the single thing that makes a metal, is this tendency to give up its electrons and not ever to take electrons in. And the nonmetals often go both ways. Sometimes they give up electrons, a lot of them, but some of them take and give electrons. Alright, so, and then we thought about some of the metals we're really familiar with, in particular iron, and we saw that iron will often give up its electrons and lose its integrity, and we call that rusting. So steel, which is made of iron, rusts, and when iron rusts, it gives up its electrons and becomes a new substance we call rust. And we'll talk about what that actually is chemically. Obviously, we can't just have iron 2+ floating around without an anion nearby, but we know that the iron is giving up its electrons. And then we were beginning to think about how we could talk about the relative ease that metals give up their electrons. And that will help explain what happened with the orange earlier, where we had maybe one metal giving up electrons, or maybe both giving up electrons and producing the voltage. We're not sure what went on, but we'll know in a minute. So, we came to our challenge, and that was to rank these metals in order of their oxidation potential. And we use the word oxidation to refer to the tendency of a metal to give up its electrons. And we're going to call that oxidation. There's a good reason for calling that oxidation. We're going to call it oxidation. And we're going to define oxidation as the loss of electrons. So we have a mnemonic to help us remember that. Leo the lion says Gur, so L-E-O stands for Leo the lion, and loss of electrons is oxidation. So if you picture a lion going around, and that lion's name is Leo, so you'll remember that he says Gur, and that loss of electrons is oxidation. Oxidation potential then is its willingness to lose electrons. Literally, potential, of course, means voltage. So we're going to use voltage as a measure of the atom's willingness to give up electrons. And we have some metals here that we should be familiar with. What metals do we have here? Go ahead and call them out.
Sodium, copper, iron, gold. Gold and calcium.
Calcium. All right, there's no silver there. We could put silver on the list if you like. Would you like me to add silver?
No.
Well, you can probably figure out silver as well. All righty. Now,
which
we're
form
going
of
to take
silver?
a clue from the way we know, what we know about these metals in real life to figure out which ones give up their electrons most easily. And we'll rank them in their order of their willingness to give up electrons, from the most willing to give up electrons to the least willing to give up electrons. It's actually called an activity series, but we don't need that name. It's called an activity series. We don't need that name, but we're going to rank these. All right, so of these metals here, which one do we think is going to be the most willing to give up electrons?
Calcium.
Copper?
Some people say copper. Now, why do you think copper is really willing to give up its electrons?
It always turns green.
Because it
Turns green?
does turn green. Okay? Copper does turn green, so we know that's undergoing a reaction, and we think the one thing metals can do to react is give up their electrons. So if copper's turning green, it must be giving up its electrons. Okay? But do we see copper turning green?
No.
You've never seen copper turn green. You just said you saw copper
But
turn
like,
green.
you see it green, but you don't...
Green and when it's
Okay, so you observe it turning to green. If you observe it, you don't observe it turning to green. It stays bright, shiny red the whole time.
It turns green, but you don't...
Okay, it turns green. All right. If it turns green, what do we know about the copper? It also exists for us to observe it in the metallic state as a solid. Right? We know solid copper turns green, therefore we see it undergo the transition of losing its electrons.
Oh, okay.
Okay? If that's the case, can it be the thing that loses its electron most?
No.
No, because we know that some atoms, some elements, some atoms, we never see lose their electrons.
Sodium.
Which ones do we never, in the natural environment, see losing their electrons?
Sodium and calcium.
Sodium. Why do we know we never see sodium losing its electrons in the natural environment?
Because it always bonds to something else
That's
really
right.
quickly.
You always find sodium bonded to somewhere else. Nowhere on the surface of the planet do you find sodium metal. Nowhere. Why do we never find in the native environment sodium metal?
It oxidizes very quickly.
Too reactive, which means it gives up its electrons
Very quickly.
easily. So, copper versus sodium. Which one gives up its electrons more easily?
Sodium.
Sodium, obviously, because by the time we meet it, it has already given up its electrons, whereas copper we can observe give up its electrons. So, sodium. Is there anything here that you think might beat sodium, but we never see it in its elemental state?
Yeah. I might say
You
calcium.
seldom see calcium in
Yeah.
its elemental state, but now we're going to have to think about our chemistry between calcium and sodium. So these are the two that are vying for the one that gives up electrons most. The others we see in their elemental state. We see shiny red copper, we see shiny iron, we certainly see shiny gold, we certainly see shiny silver in their native state. But these two we never see in their native state. Which one do you think might be more reactive? Well, what about their positions on the periodic table? Can
Calcium.
that give us a clue?
Yes.
Sodium has to give up how many electrons?
1.
Calcium has to give up how many electrons? 2. We know that from our periodic table work. So now, which one do you think gives up electrons more easily?
Sodium.
Sodium does. If you look at its position on the periodic table, you understand the number of electrons it has to give. Sodium has the highest oxidation potential. It gives up its electrons most easily. Well, if that's the case, what must be number 2?
Calcium.
Calcium. Great. We've got 2 of them sequestered away on our list. All right, so we've got sodium and calcium taken care of. Now we're between copper, iron, and silver.
Iron next.
You think iron is next? Why do you think iron is next?
Because it's easier to see rust
Yeah,
than it
you
is to
see
see
rust a
the
lot more often than
green.
you see a patina on copper. Right? We see rust a lot more often. In fact, around on nautical instruments, do we often use steel or copper? On nautical instruments, things that are going to ocean-going vessels or things that are in contact with water. Do we most often use iron for that or copper for that? Copper. We use copper much more often if things are in contact with fresh water or even salt water. Why do we use copper more often?
Because steel would rust faster.
Steel rusts more quickly than copper. So boats often have copper fittings rather than steel fittings because the copper lasts longer in contact with an oxidizing environment. All right, so next we're going to put down iron. That must be our next one. It certainly is rust easily, so we suspect that it's our next in terms of oxidation potential. Question?
What did you call the electron losing of silver? Something with a P?
Oh, a patina. A patina is when you have a metal that's not very reactive, but it still forms a layer of oxide. We call that a patina. So we use that for copper and for silver. If silver forms a patina, it becomes black and discolored if you're not careful to polish your silver jewelry. And copper certainly forms a patina. And copper patina is quite attractive because it's green. Right? So you see a shiny copper roof go on usually an important building, a monumental building, and then over the course of several months, it gradually turns green, and that, in fact, is what we're looking for. Okay, so it's called a patina. And I have an interesting story about that that I'll share in just a minute. All right, so sodium, calcium, iron. What do we have left now? We've got iron placed. Now we have
Copper, gold, and silver.
copper, gold, and silver.
Copper.
You want to put copper next. Why?
I've seen more green roofs than I've seen black on silver.
Exactly. You see more green roofs than you see black on silver. In fact, silver tends to preserve its shininess, for a fairly long period of time. You have to polish it eventually, but certainly not like you have to polish copper. Okay? And okay, now we're up silver and gold for our last two. We've got silver versus gold.
Silver.
Silver gives up its electrons more easily, and one way we know that too is it's not quite as valuable as gold, because gold's value partially is because
It stays pure.
it stays the bright, shiny metal. That's one of the reasons it's so valuable. We make jewelry out of gold more often than we make it out of copper. Copper jewelry is quite nice, but you have to polish it way more often than you have to polish your gold jewelry. Okay? So all these
Yeah, I've never
elements
had to.
have different oxidation potentials. We put numbers to these in a minute, but we understand that sodium is going to very easily give up its electrons, and gold is going to be very difficult to give up its electrons. In fact, gold tends not to give up its electrons. So one of the ways to preserve things is to put a fine layer of gold electroplate on the outside. That would preserve it, as would copper or as would copper plate. Another thing we know about gold is we make jewelry out of gold, and it's been valuable throughout history because it retains its shiny surface, so it's decorative. Okay, and I find it really, really more decorative than copper, really, if you think about it. But it's gold, and so it stays that nice, bright, shiny color. Yes.
But it can blacken after a long
Yes,
period
it can, but very rarely does it. And that's one of the ways you know you've got real gold jewelry, is it doesn't tend to oxidize.
Nice.
Good. All right. So this is our oxidation potential. So if these elements have different tendencies to lose electrons, we can talk about them shifting electrons between each other. So let's give ourselves a scenario here.
Look for GERD.
Yeah.
Yeah, what about GERD? Let's give ourselves a scenario here. Let's grab calcium and copper. So we're going to be a little bit careful writing our A's and our U's. And on one side we have calcium, and the other side we're going to have copper. And we're going to have copper metal, and we're going to have calcium metal. So we're going to be a little careful with our calcium metal because we know that if water is around too much, or even if it stays in contact with air too much, it's going to oxidize. So we're going to be a little bit careful with our calcium metal, but we've set up this situation in which we have calcium, and we have calcium ion present, and we have copper, copper ion, so we got the Cooper ion here, and we have the copper metal present. Okay? One way of thinking about this interaction is thinking about a competition for electrons.
Who's gonna win?
Okay? This copper solid has electrons that it could give up to the calcium and go to copper 2+, right? This reaction could occur where the copper solid becomes copper 2+ and liberates a couple of electrons. Similarly, calcium could become calcium 2+, and that would also liberate 2 electrons. So one of the ways I like to think of what's going on in these electrochemical reactions is this competition for electrons. There's a possibility of either of these two producing electrons. Right? So what we're really asking is calcium 2+ or copper 2+ more likely to gain those extra electrons? Which one is going to pull on those electrons?
Copper. Oh.
And to help us think through this,
Okay, no,
Calcium
no,
2+.
copper.
here's,
Okay, I figured.
okay, why?
Because copper has more protons.
All right, copper is a larger atom, it's got more protons, its attraction for those electrons is greater. Absolutely correct.
I was right?
Yeah, absolutely correct. Another way of thinking of it is you know that every chemical reaction is reversible. Right? So we have 2 chemical reactions. When we made this series, we made a reversible chemical reaction. We said calcium, copper has more protons than calcium, so copper will attract electrons. We said that calcium can become calcium ions and liberate 2 electrons. We said that copper can become copper ion and eliminate and release, 2 electrons.
Wouldn't it be minus?
No, the
Oh,
metal
yeah,
ions are
yeah.
always positively charged and the electrons are negatively charged. Okay?
Yeah.
And we know that both of these reactions take place. But we know that one of these reactions is more favorable. Which of these reactions is more favorable? Yes?
The metal with less oxidation potential.
That's right. No, and with the greater oxidation potential. This is the more favorable reaction.
Why?
Tell me. Why is this a more favorable reaction?
It'll give it up more easily.
Yeah, this one releases electrons more easily. That's what we spent the time making this activity series to demonstrate. So this reaction is more favorable than this one. They both happen, but this is more favorable than this one. Calcium will give up its electrons more than copper. Yes?
I'm having a hard time seeing how oxidation potential isn't just an inverse relationship with electronegativity.
Well, you're still trapped in thinking about electron negativity. Electron negativity is electron attraction ability. So while we can give electron negativity numbers for metals, we don't. Because metals tend to release their electrons. So we're not talking about electron negativity, we have to talk about oxidation and in minute reduction potentials of metals, because that's more in line of what we need to talk about.
But one's an attraction, one's a release. So aren't they?
We use electron negativity for electron attracting ability, which is very useful if we're going to talk about covalent compounds. In this case, we need electron negativity to explain the bonding and the electron density between fluorine and oxygen. You remember, which is more electronegative, fluorine or oxygen? Fluorine, which means the electrons will hang out more with the fluorine than they will with the oxygen.
Did you catch that?
Which is more electronegative, oxygen or hydrogen?
Ooh,
Oxygen, which means the electrons will hang out more with the oxygen than with the hydrogen. That's how we can make good use of electron negativity. We're not transferring the electrons, we're saying you've got a covalent bond. What's a covalent bond? Electrons are shared. So when we have a covalent bond, electron negativity is going to help us figure out where those electrons are spending their time, closer to the more electronegative element. Do we have a covalent bond here? No. So electron negativity is not what we need here. We need something else. We need a measure of how easily these things give up their electrons. And what do we call that? Oxidation potential. Right? That's what we need to talk about this. They're not sharing electrons. We consider ionic bonds a giving of electrons, a release of electrons. So we need oxidation potential. Question?
So the easier the release of the electrons, the greater the oxidation.
Absolutely. Yes.
So for the first two metals, sodium and calcium, we use ion charges to determine which one has higher oxidation potential.
Well, actually, what we'll do, in reality, we can do this experimentally. We thought our way through this by what we knew about their placing on the periodic table. But in reality, we would do this experimentally, or we would just look at a table. Okay? When we talked about these things, when we ranked the activity series, we were just using what we knew about the metals. So we did that to connect your everyday knowledge to chemical knowledge, which is a good thing to do. Chemistry isn't an abstract science, it's about real things that we encounter. So one of the things I wanted to do was have you think about, oh yes, these elements exist all around us, and they behave in our environment according to their oxidation potentials. Some of them we keep for jewelry, some of them we put in cars and it rusts despite us, some of them we use for piping, but we do all of that because of their oxidation potential. We didn't think of it, but now we can think of it and put some theory behind what we already knew about these metals. Yes?
So it's like K in the sense that it's empirical.
Yes, it's the actual numbers are determined, but we have a good theory behind this, so it's not like K at all. You're talking about K, the equilibrium constant. That is empirical. It works because it works, and there's no theory behind it. There's good reasons, and in fact we use them to compare copper and calcium. We have good theoretical reasons for understanding what we observe. Number of electrons, number of energy levels, number of protons. So it's not like K at all. Right? Sure, we can measure them empirically, but our theory gives it to us as well. In fact, we're soon going to jump to the theory, but it's good to take the theory and always go and see if it works in the real world. Of course, that's the test of a theory. Does it actually work when we go to look at these metals? Okay? Alrighty, so this is more favorable of these two reactions. I'm going to give you another reaction now. Another couple of reactions, still based on this scenario where we've got calcium and copper competing for electrons. I'm going to say, I'm going to turn these reactions around. I'm going to take two electrons, and I'm going to give that to calcium to produce calcium metal. And I'm going to take two electrons, and I'm going to give those to copper to produce copper metal. Which of these two reactions is most favorable?
The bottom one.
Why?
Because copper will more easily attract electrons than calcium will.
If this is less favorable going this way, then it's certainly more favorable going in reverse. We know that reactions are reversible in the physical. So this means that this reaction is more favorable. Now let's look back at our original scenario. In our original scenario, we had calcium metal and calcium ion. We had copper metal and copper ion. And we said, okay, the possibility of giving up electrons is there. So we have all kinds of possible reactions. We can have calcium giving up its electrons, or copper giving up its electrons. We can have calcium taking electrons, or copper taking electrons. So we have 4 possible reactions. Which reactions take place?
Copper taking in
We've already decided that, because we looked at the possible reactions. Which one is the right one for releasing electrons? It's the one where the
Calcium.
element with the greater oxidation potential releases electrons. Which one is better for accepting electrons?
The one with the lesser
The
oxidation.
one with the lower oxidation potential is going to be better at accepting electrons. Those are our 2 reactions. So let me reiterate how we did this. We took the 2 metals and we looked at the possibilities. We have calcium solid and calcium ion. Copper solid and copper ion. And we put down the possible reactions. What are the possible reactions? Calcium giving up its electrons, copper giving up its electrons. The other possible reaction is calcium accepting electrons, copper accepting electrons. Right? Those are the possible reactions. So it seems really confusing if you're like copper ions and copper metal and calcium metal, all these things. There's only 2 things. Either it gives its electrons or it takes the electrons. Right? Only 2 things. It either gives the electrons or it takes the electrons. And there's only 2 metals present. Right? There's the calcium and the copper. So either the calcium gives electrons or the calcium takes electrons. And either the copper gives electrons or the copper takes electrons. So it sounds like there's a lot of stuff going on, but really either giving electrons or taking electrons. Right? And it's either the copper that does it or the calcium that does it. And all we needed to do to figure out what happens is we went back and we said, well, wait a minute. Copper likes electrons more, let me anthropomorphize, than calcium. So who's going to get the electrons?
Copper.
Copper. It likes electrons more than calcium. Who's going to give up the electrons?
Calcium.
Calcium, because copper likes electrons more than calcium. The same reason gives you everything. If copper likes electrons more than calcium, then calcium will give up its electrons and copper will get the electrons. What about if we had silver and iron? We have silver and we have iron. What would happen? Yes?
Iron will give up its electrons and silver will keep it.
Pretty good, that's correct. Iron will give up. What if we had sodium and calcium? Give up its electrons?
Hold on to our track.
What if we had gold and silver?
Very close that silver would give it up, and then copper would. Silver would give it up.
Silver would give up its
Gold would
electrons,
attract.
gold would take its electrons. Okay? So it looks like lots of stuff going on. Who wants the electrons more gets them. Yes?
What if the 2 metals are from the same family? So
They
they're
still have different oxidation potentials.
okay. So let's say potassium and calcium.
Yes. Well, they're not in the same family. How about magnesium and calcium?
Magnesium and calcium.
Which one has more protons?
I would
It's
have
okay to check the periodic table, sorry.
I don't have.
Which one has more electrons? Magnesium or calcium?
Yeah.
Calcium. So which one is probably going to take electrons more?
Magnesium. Oh, yeah.
The one.
Magnesium will give them up.
Yeah, calcium will get electrons from magnesium because calcium has more protons. So even in the same family, we can still use our theory to rank them.
Okay.
And gold and silver, I believe, are in the same family too, are they not?
Oh yeah, they are.
Yeah, they are in the
Yeah.
same family, right? So we know what's going on. All right. All right. So what I just did by finding the reaction, you're going to do. I'm going to give you copper and iron. Well, it's an awful lot like what we did in the lab the other day, isn't it? We have copper and iron, right? Copper and iron strips. I think we used zinc maybe. But we have copper and iron, and we stuck them into our little battery. Tell me the reactions that are going to happen. And you have to assume that once we stuck it in the orange, the ions were present. So we had calcium present, so we had copper present, and we had copper 2+. We had iron present, and we had iron 2+. Right? The whole point of that was that we needed those ions. So we put them in something acidic to make sure we have some ions. Because once we get some ions, we can get electrons going back and forth. So write the two reactions that are taking place. We put calcium and copper and copper ions mirrored with iron and iron ions. What happens?
Oh my. Well, it's really close.
Oh, you're supposed to do it back. Did you guys bring that?
I don't know. I left that to my brother.
Didn't you have like a whole shoebox of them?
Yeah, I left them all here, and then I took them all home to clean them and stuff. Because I wasn't gonna need them for fine arts anymore, so I don't know if they're here. If he brought them or not.
All right, so I went through and I figured out either one of them is gaining electrons or one of them is losing electrons or whatever. So two possibilities for gaining electrons, two possibilities for losing electrons. What happens?
Oh,
What happens? Yes?
I'm gonna say that copper releases its electrons, and then iron takes up those electrons.
Okay. Which one did we decide had the greater oxidation potential?
Iron.
Iron.
So iron gives it up,
Other way
and
around.
copper takes
Okay, so what do you mean by other way around? Let's just be explicit
So
about it.
iron will release its electrons.
So
and
you think
copper-
iron will give up its electrons
Yeah. and copper will take up those
copper will gain
electrons.
the electrons? I concur. Those are your reactions. Alright. So,
Do you not like the taste of coffee?
It's cold now.
Oh.
alrighty. So, which one is being oxidized? Iron is being oxidized. Let's write that down. Iron is being oxidized. Iron is being oxidized. Right? Iron is being oxidized. What's happening to the copper?
Reverse?
It's the opposite of being
Is
oxidized.
there a word for
All
it?
right.
Being reduced.
Here's, we
Reduced.
need a name for this, don't we? Right? We've got idea of losing electrons as oxidation, but we need a name for the reverse process. Any ideas?
Reduction.
Why reduction?
Because you said it already.
Well, why reduction? What is being reduced in a reduction? Speak up.
the electron charge.
Copper goes from being 2 plus to
Oh.
0. Is that coming down?
Yes.
Yes, it is. So in a reduction, which is a really good name for this, we are bringing the charge down. We are reducing the charge. That gives us the name reduction. So copper
Gir's gaining of electrons.
is being
Reduced.
reduced.
Oh.
So we have an oxidation and a reduction, and lo and behold, we call this section redox chemistry. Because in order for an oxidation, there must be a reduction. And in order for a reduction, there must be a oxidation. Ever see an electron?
No.
No.
Me neither, except for a fraction of a second in a lightning storm. That means electrons are always going from atom to atom. Right? You don't see them knocking around, hey, I'm an electron, I have no home. Doesn't happen. They always go from atom to atom. If that's the case, then if something gives up its electrons, something else must be
Losing
gaining
them.
the electrons.
Oh.
The electrons don't stay free. They just don't. They always go from one atom to another. So an oxidation is always accompanied by a
Reduction.
reduction. A reduction is always accompanied by a...
Oxidation.
How can we remember this?
Leo the Lion says grr. Did they actually growl?
That was not smart.
Leo the lion says grr. And what does grr tell us? Yes?
Gaining of electrons is reduction.
historical note. Oxidation got its name from the fact that oxygen really likes electrons, and so when you put oxygen next to almost any metal, it'll take the electrons from the metal.
Oh,
So
fire.
that metal becomes exposed to oxygen
Fire.
or oxidized. So you put oxygen next to any metal, iron, copper, whatever, it'll take the electrons from the metal and therefore oxidize the metal. So exposure to oxygen, causes you to be oxidized. And that gave its name to the process. Reduction got its name from
Losing the
you're
charge.
losing the charge. So that's oxidation got its name for, it's just like being exposed to oxygen. Reduction got its name from, you reduce the charge. Yes?
Did you come up with this,
I wish I had. I did come up with, I saw a red cat. We won't get to that for a couple of days. I saw a red cat.
No, but Mickey Mouse is always.
Okay, which will help us on the next step. That was my mnemonic, but we're not there yet. All right, so where are we going here? Okay, so now we know that reduction is a loss of charge number. We can look at atoms, and we can give the charges on the atoms in compounds using this whole principle of, well, the charge is some number that the atom has, and we could, in theory, reduce it. So we're going on to our next topic now. Our first topic, we've just finished, is this idea of redox. So let me summarize that before we get to this next bit about charge. Redox. And that means reduction, oxidation. So that was our first concept that we're just finishing. Redox is oxidation reduction. That means one element or species, because it can actually happen to a complex of atoms. One element is reduced while the other is
Oxidized.
one is reduced while the other is
Oxidized.
oxidized. Yes, in the back.
The element with the least number of protons, is that
No, we had to rank them. It's not all about number of protons,
Oh,
is
it's
it?
not, okay.
Right? It's not
So
always
we
about
can't think
number
of
of
it like
protons.
that.
You cannot think of it like that. It's there's more to it than that.
Okay.
Because it's also energy levels.
Uh-huh.
Also energy levels.
Quanta.
You're right, protons make a big difference. That's